This lesson deals with a JFET as a voltage-controlled resistance and as a current source. You can find these notes in the ECE302 ebook in Chapter 4, starting on page 23. In the ohmic region of the JFET, we have this expression for I sub d, and we plotted it here, and it's basically this straight line that begins to turn. We're plotting I sub d versus VDS, and here's I sub d and here's VDS. That's like an Ohm's law equation except for this term right here. In fact, this term is causing that little bit of turning, creating this parabolic effect. If we keep the drain source voltage small enough so that when it's squared, it's small compared to this quantity, then we could drop it out. And our equation would just be that I sub d is K times the quantity 2 times VGS minus the pinch-off times VDS. We're going to evaluate this at some operating point, and we're going to be operating basically in this region over here where we have pretty much a straight line. We've got the current I sub d in terms of VDS. This would be 1 over resistance. I'll call that little r sub ds. And it's equal to the reciprocal of this equation when the gate source is greater than or equal to pinch-off. When the gate source is less than or equal to pinch-off, this becomes zero current and the resistance goes to infinity. The same thing will happen here when the gate source equals a pinch-off. Let's use this to make a voltage-controlled attenuator. Attenuator is a term that refers to a voltage divider, and they refer to the attenuation as the reciprocal of the voltage division calculation. That makes it a positive dB term. Well, they're actually making the voltage smaller in size. I've got my JFET, and I've got a control voltage here. I'm going to make it so that it's negative when V sub C is positive. We're going to be forming a voltage divider. And suppose that for this JFET, IDSS is 16 milliamps, and the pinch-off is minus 4. That would make K 16 divided by minus 4 squared, or 1 milliamp per volt squared. Our value of RDS would then be 1 over 2K, so 2 times 1 milli. The gate source voltage is going to be minus V sub C, and the pinch-off is going to be minus 4. Suppose we plug in V sub C equal to 0. The gate source is greater than pinch-off, and this expression then is 1 over 2, 0 plus 4, and the reciprocal of that is 125. There's a voltage divider with a 10K resistor of 125 over 10K plus 125, and that's 1 over 81. It's made 81 times smaller. If we let the control voltage be 2, we're still greater than pinch-off. And now we've got here a minus 2 plus 4, so we've got a plus 2. The reciprocal of that is 250 ohms. And that voltage divider is 1 over 41. It's 41 times smaller. If the control voltage is equal to 4, that's equal to the pinch-off. That's going to make this expression 0 in the denominator, so the reciprocal is infinity. So a big number over a big number plus 10K is basically 1. And then if you were to apply, say, 6 volts here, which is less than pinch-off, we'd be cutting off the transistor, and that would still make the resistance infinite, and the gain would again be 1. In other words, we're going to be passing the signal. Let's take a look at the VI characteristics of that transistor on the previous page near the origin. We'll do the curve tracer using the value for IDSS and the pinch-off, so a VTO of minus 4, and we calculated beta to be 1 milliamp per volt squared. But now let me vary VDS from minus 0.7 to plus 0.7 with 200 points. That'd be 7 millivolts per step. And then do our voltages from 0 to minus 4 volt in 1 volt steps. The results are shown below. And as we expect, the slope here for the gate source of 0 is about 125 ohms. And then as we make the gate source more negative, then the resistance gets higher and higher and higher. But watch what happens here. As we begin to go negative on the drain source voltage, all of a sudden current starts to flow. In fact, it's coming out of the drain. Let's go back over here and see what happens. When this is 0 volts, the drain source voltage is across here. And that means when that's negative, we're going to forward bias this diode and current's going to flow in this direction. Current would be coming out of the drain, going into the gate. This is a limitation of the range of voltages I can apply when they swing negative. As a voltage-controlled resistor, we're going to expect to see signals that are most likely sinusoids or things that swing positive and negative. The worst case here is the case of the gate source being equal to 0. All of these will have the same type of behavior. For a gate source of 0, we had an attenuation of 81. So the output is 1 over 81 times the input, but the output is the drain source voltage. And that needs to be greater than or equal to minus 0.6 volts. Solving this equation for Vn, we could say that Vn then needs to be greater than 81 times minus 0.6, which is minus 48.6 volts. Our voltage-controlled attenuator will work for a gate source controlling voltage of 0 if we make Vn greater than minus 48.6 volts. Let's test our voltage-controlled attenuator by doing a piece-by simulation. Hook up an input voltage and I'll make a sine wave of 1 kilohertz with a peak value of 2 and an average value of 0. Put a 10K resistor here between nodes 1 and 2, controlling voltage between 0 and 3. I'll let it be 0 initially, the default, and my JFETs between 2, 3, and 0, and then my JFET parameters. Let's plot 2 cycles. So 1 over 1K is 1 millisecond, so that would be 2 milliseconds. If you divide that by 200, you get 10 microseconds. We'll start printing it times 0, and we'll do a sealing step the same as the print step to get a nice smooth result. For a gate source voltage of 0, we would expect a gain of 1 over 81. If you take the peak of 2 volts and divide it by 81, you get 24.763 millivolts, and that's exactly what we measure right here. The attenuator is working. I'll run the same simulation, but now make the controlling voltage equal to 2 volts, so the gate source is equal to minus 2. Again, we get an attenuation, and the peak here is a little bit less than 50 millivolts given a 2 volt input, and that's approximately Vn divided by 41. Run the simulation again with the control voltage equal to 6 volts, which would put us into cutoff, and the output equals the input. Our attenuator is working as we expected. We saw on page 24 that when the JFET was used as a low resistance, we needed to keep the input from getting too small, in other words, too negative. Otherwise, the drain to gate diode would turn on. Is there any such limit when the JFET is in the off state? Let's investigate this just by running some simulations. Suppose that I rerun the last simulation with a 4 volt sine wave instead of a 2 volt sine wave. Well, here's the output for a 4 volt sine wave. We see that the bottom half of the sine wave is distorted. See, and figure out why. I plotted the gate to drain voltage, and I also plotted the pinch-off voltage. So here's the plotting of minus 4, which is the pinch-off voltage, and here is the gate to drain voltage. So here was the gate and here is the drain. And you can see that the gate to drain is varying. Now, to be in cutoff, the gate source needs to be less than or equal to pinch-off, and it is, but so does the gate to drain. Here's the pinch-off, and here's where it is less than or equal to that. And when that's occurring, we get a perfect sine wave out with a gain of 1 in our circuit. But here we see that the gate to drain is actually greater than pinch-off, and that's where things stop working. Let's investigate what happens to the gate to drain voltage for different values of the input. To be in cutoff, the gate to drain needs to be less than or equal to pinch-off, and the gate to source needs to be less than or equal to pinch-off, but the gate to source is fixed at minus V sub C. When the JFET's in cutoff, the output roughly equals the input. The gate is equal to minus V sub C, and the drain, which is equal to the output, is equal to approximately Vn. So we can calculate the gate to drain voltage as the difference of those two. So minus V sub C minus Vn, and that needs to be less than or equal to the pinch-off voltage. So that says that the input voltage, you bring it over here, needs to be greater than or equal to minus V sub C minus the pinch-off. So if we had a control voltage of 6, the input would need to be greater than minus V sub C minus the pinch-off minus 6 minus a minus 4 or minus 2. When we had the 2 volt sine wave, everything worked fine, but when we had the 4 volt sine wave, then we ran into trouble. We could predict that with this equation. If you were to have the control voltage of 4, that would be having you right at the pinch-off voltage. We would have then our input needs to be greater than minus 4, minus a minus 4 is 0, so it can only be a positive voltage. Solving this equation, bring this over here, then V sub C needs to be greater than or equal to minus Vn minus V sub P. Now Vn's varying, so I'll pick the minimum value and then take the negative of it. Let me do an example. If I had a 2 volt sine wave, I would then pick V sub C, the controlling voltage, to be greater than or equal to minus, and then my input was a 2 volt sine wave, so it swings down to minus 2, and then minus a minus 4, or 6 volts. That's what we did. We put a 6 volt voltage on there when we had a 2 volt sine wave. We might have to place a voltage limiter across our input to clip the waveform so that we stay within these boundaries. We can also use the JFET as a current source. In fact, this is the symbol for this particular circuit. It's a circle with a bar. The voltage is labeled as V sub x and the current I sub x. This is sort of our symbol for a diode, but with a circle. It indicates that current can flow in this direction, and the circle is indicating that it's a current source. The circuit that's between these two terminals is a JFET and a resistor R. If you plot V sub x versus I sub x, you get a curve that looks like this. I'd like to solve for what is I sub x and V sub x if we had a JFET where IDSS was 20 milliamps, the pinch-off was minus 6, and we use a 220 ohm resistor. To solve any equation in the ohmic or saturation region, we're going to need to know the value of K, which is IDSS over the pinch-off squared. IDSS for this particular transistor was 20 milliamps, and the pinch-off was minus 6, and that turns out to be 0.556 milliamps per volt squared. In saturation, the drain current is equal to K times the quantity of the gate source minus the pinch-off voltages squared. K is 0.556 milli, the gate source, and then we've got the pinch-off of minus 6. So I have one equation and two unknowns. I can get a second equation from the circuit itself. Let's go back to the previous page and see if we can find that equation. Here's where the gate source voltage is, and that voltage is the voltage across here. The gate source voltage is the drain current times R, but with a minus sign. So that's what I have over here, that the gate source voltage is minus ID times 220, the resistor that was specified. I've got two equations and two unknowns. Let me solve for the gate source voltage by taking this first equation, which is here, and substituting in for the value of I sub D from this equation, which is the gate source divided by 220 with a minus sign. Let me square this. I get the gate source squared, inner product times 2, so that's 12, and then 6 squared or 36. I'll bring this on the other side of the equation. I'll bring this over here as minus VGS over 220 divided by 0.556 milli. That's equal to minus 8.18. I'm going to bring that on the other side of the equation and add 12 to that. I have 12 plus 8.18, so that's 20.18. I have VGS squared, 20.18 VGS plus 36 is equal to 0. We can now solve this by using the quadratic equations. The gate source voltage is equal to minus this term, plus or minus this term squared, minus 4 times 1 times 36 divided by 2 times 1. I got two solutions. I got a minus 1.98 volts and minus 18.2. To be in current saturation, I need to have the gate source greater than pinch-off. This one here is greater than pinch-off. Minus 1.98 is greater than minus 4, but this one isn't. I'm always going to get two solutions. I have to throw away one of these two, and this is going to be the difficult part for computer software like SPICE. In this case, the solution of minus 18.2 is inconsistent with the assumption that we were in current saturation. So we'll throw that one out. Our gate source voltage then is a minus 1.98. Our drain current then is equal to K times the gate source voltage minus pinch-off squared. And that turns out to be about 9 milliamps. That's the value of our current when we leveled out. We went into the active or current saturation region. Voltage V sub X is equal to minus the gate drain voltage. Let's go back to the previous page and see that. So the voltage from gate to drain is here. And because of this short circuit, that's the same voltage as V sub X, but with the opposite sign. That's where that equation came from. At the point V sub X on, that's where the curve starts to level off. The gate drain is equal to the pinch-off voltage. That's our transition point between the ohmic and the current saturation region. This voltage then is equal to minus V sub GD. That's equal to minus V sub P, so minus a minus 6. So that occurs at 6 volts and about 9 milliamps. So that circuit that we looked at has a VI characteristic that eventually the current becomes constant at about 9 milliamps when the voltage reaches about 6 volts across it. Let's verify our results by doing a SPICE simulation. So here's my current source. I'm going to hook up a voltage source. I'm going to put a limiting resistor here so I can limit how much current comes in. I've got a title, got a comment, got a voltage source between 1 and 0. I'm going to do a sweep, so I'll just set that equal to 0 for right now. And then my resistor here is 220 ohms, and my JFET's between 2 and ground and 3, so 203. Just call the model mod. And then my pinch-off voltage was minus 6, and my value of K was 0.556 milliamps per volt squared. I'm going to sweep the voltage here from, say, 0 to 20 volts and do 200 points. That would be 10 millivolts per step. We take a look at the results on the bottom. And we can see we come up, and eventually we limit the current, and it becomes constant. I used to use this circuit as a current limiter so that we could have current flowing through a circuit, and all of a sudden we would stop if we exceeded a certain point. That's sort of like what we do in lab when we set the current limiter on a power supply. Here it also gives you a current source of about 9 milliamps once you get to 6 volts. If you were to take the resistor R of the 220 ohms and make it a short, you just get IDSS, and then V sub X on would be at minus the pinch-off voltage. So you can create a variable current source by putting a pot where R is. And this is using the JFET as a voltage-controlled resistance and as a current source.